In this video, we'll go through the idea of an equivalence relation. So suppose we have a set A, and then we construct a relation which is a subset of the Cartesian product of A with itself, and the relation R is an equivalence relation if R is simultaneously reflexive, symmetric, and transitive. And it's really that simple. An equivalence relation is simply a relation that is reflexive, symmetric, and transitive. So before I move on to show you an example, let's do a brief recap of what it means for a relation to be reflexive, symmetric, and transitive. So I'm going to use some logical symbols here to save myself some time. So for a reflexive relation, that means for all, so this symbol here means for all. So for all x that are elements of A, the ordered pair xx is an element of R. So if this statement here is true, then your relation is reflexive. Now for a symmetric relation, we get for all x and y that are elements of A, if x, y is an element of R, then this immediately implies that the ordered pair yx is also an element of R. So if this statement here is true, then your relation is symmetric. And now we also have for all x, y, z's that are elements of A, if we know that x, y is an element of R, and yz is an element of R, then this immediately implies xz is an element of R. And if this statement is true, then your relation is transitive. So I've covered these concepts in the previous 3 videos, so this is just a quick recap, and now I'm going to move on to an example of an equivalence relation. So for our example, we're going to construct an equivalence relation, and then in order to do that, we need to first identify our set A before we can construct our relation. And then for A, we're going to use the set of real numbers, which is represented by this symbol. So this is the set of numbers, such as the square root of 2, pi, 1, 0, and so on. So we're going to use the set of real numbers. And then from the set of real numbers, we can construct R, our relation, which is just a subset of the set of real numbers with itself. And then we're going to define R in such a way. So R is the set consisting of the ordered pairs xy, which are members of the Cartesian product of the set of real numbers with itself, such that x minus y is rational. So x minus y is a member of the set of rational numbers. So this symbol here represents the set of rational numbers. And a rational number is a number that can be represented as a fraction, where say for example, if x is a member of the set of rational numbers, then x is equal to a fraction where a and b are integers. So a and b are whole numbers. And so our relation is a relation where x will be related to y if the difference of x and y is rational. So say for example, 2 is related to 3, because obviously 2 minus 3 is negative 1, which is rational. So for this relation, 2 is related to 3. On the other hand, 2 is not related to the square root of 2, because 2 minus the square root of 2 is irrational. So 2 is not related to the square root of 2. But on the other hand, the square root of 2 plus 1/2 is related to the square root of 2, because if you take the difference, you get square root of 2 plus 1/2 minus square root of 2, which is just equal to 1/2, which is rational. So this number is related to the square root of 2. So this is how this relation works. And now we're going to show that this relation is actually an equivalence relation. So now we've defined a relation where two numbers are related to one another if their difference is rational. And in order to prove that it is an equivalence relation, we need to check that this relation fulfills these 3 statements. So first of all, we need to show that this relation is reflexive. So that means we need to show that for all real numbers, every real number is related to itself. And as you can see from this definition, for a number to be related to another number, its difference needs to be rational. And as you can see, for any real number, you can see that its difference is always equal to 0, because any number subtracted by itself is always 0. And this is definitely a rational number. And so from this definition, you can see that for this relation, every number in the set of real numbers is related to itself. And so this checks that their relation R is reflexive. So we've nailed this first condition already. Now let's move on to the second one. We need to prove that the relation is symmetric. So we need to show that for all real numbers x, y, if x is related to y, then this also means y is related to x. So now let's go back to the definition of the relation. So if we know that x is related to y, then that means x minus y is a rational number. And does this immediately imply that y is related to x? And that is of course true, because if we want to know whether y is related to x, we just need to check whether y minus x is rational. And since we already know that x minus y is rational, y minus x is just negative of x minus y, which is of course rational. So a negative of a rational number is of course also rational. So here this checks that this statement is indeed true. So if x is related to y, so if x minus y is rational, then y must also be related to x. So y minus x must also be rational. And so this checks that our relation is also symmetric. So we've nailed this second condition as well. So now the final thing we have to do is to check that this relation is also transitive. So now for the last part, in order to show that our relation is transitive, we need to show that for all real numbers x, y, z, we need to show that if x is related to y, and if y is related to z, then this immediately implies x is related to z. And in order to show this, we first suppose that this statement is true. So first we know that x was related to y, so x minus y is a rational number. And we also know that y minus z is also a rational number. Now we need to show that x minus z is a rational number. So we want to show that x minus z is also a rational number. So we don't know this yet, but we want to show that this is also true, if these two statements are true. Now in order to show that this is true, first we take a look at these two expressions, and let's try adding these two expressions together. So on the one hand we have x minus y, and here we also have y minus z, and as you can see we get x minus z plus negative y plus y, and of course this is just 0, so this is just x minus z. So here we have a rational number, x minus y, plus another rational number, y minus z, and then we get x minus z. And when you add two rational numbers together, of course you also get another rational number, because you can just use your simple rules of adding fractions. So if you have these two rational numbers, you can just add everything up, and then you'll just get another rational number. So of course x minus z is also a rational number. And so that shows that if x minus y is rational and y minus z is rational, then x minus z must be rational. So according to our relation R defined in such a way, if x is related to y and y is related to z, then this immediately implies x is related to z. And so this checks the third condition. So this proves that our relation is also transitive. And so this concludes our proof. We have just shown that this relation here is simultaneously reflexive, symmetric, and transitive. So this is an equivalence relation.